write down this, simplify, this comes from the Navier-Stokes energy and the energy conservation law. We have a lot of simplify, assume, consider about that, and write down this simple formula. If you want to totally exact in a real situation you want to write down, you have to write down the Navier-Stokes formula has about 10 parameters, and you have to give integral and differences between them. You cannot use this simple equation for this complicated situation. If you want to calculate that, I will give you another Navier-Stokes equation. You cannot understand some part of that. How can we use this simple equation for this complicated situation? At first, we have to consider the simple situation. We found the gist of information, and after that, step by step, we can improve our knowledge about some term and develop these terms. Maybe we consider the velocity is not changing from this point to this point. But we know exactly, we have a maximum velocity here and zero velocity here. That means we have a curve here, but we consider it as a number, as a constant number, average number. You see, the pressure also changed from this point to this point, total pressure. We have a curve over there, but we consider it as a constant action. For the turbine, if the turbine is working in high speed, the efficiency is more, and the energy gives to us is also high. How can you calculate it? It's related to this differential velocity. If the velocity between these 2 points changes, the differential of velocity increase, this turbine work increase, this pump work increase. We use a lot of simplify, assume, for write down this one. Just we are allowed to, for the simple point, these 2 points, maybe you have a pump here and want to transfer liquid to a high level for a vessel here. You can write down from this point and this point. In this situation, you can use the Bernoulli equation. Okay, write down the Bernoulli equation across the orifice, please. These 2 points are the same. Name please point 1, point 2. Yeah. For the point 1, write down the Bernoulli equation at first. P2 on rho g plus V2 power 2 divided to 2g plus Z2 plus friction factor and turbine factor. Friction and plus turbine. Yeah, also we don't have pump here, but we have to write down the formula completely. Okay, which parameter is 0? Which parameter you know we have not in this system? We have pressure differential here. Okay, we have to keep the pressure, the velocity, elevation is the same as this one. Okay, we have pump here in between. We have pump here, which in this section, which part you install a pump? We have not pump. And also the turbine. The friction, we have friction. This is like a 5 centimeter line. How can you calculate for a 5 centimeter line friction? Yeah. The pressure in the second section decrease. Write down the remaining parameter here. P1 on rho g Okay. The velocity, if in this point we have Q1 here, what about the Q here? It's equal less than or more than Q1. Q2, we have to discuss about the Q. No, it's equal. When Q2 is a little bit less than this one, that means you have accumulation around here. We have pressure drop, not velocity instead of pressure drop, velocity increase. Always be remind, my man, when we have inlet line in a black box, like orifice, pump, compressor, on all of the equipment, you have outlet line. If Q1 is more than Q2, that means you have an exit line here. You have exit line here? No. The flow rate in these two sections is equal, and the diameter refer to momentum, to mass conservation law. Q1, that means Q1 is equal to Q2. Rho A V in situation 1 equal to rho A V in situation 2. The rho is constant, the A is constant, that means the velocity is constant. Why you write down the velocity?